We have been chasing this idea of an infinite context window for what feels like years now, treating it like the holy grail of AI.
It's been the goal, for sure.
But there's this massive paradox emerging. Just making the window bigger seems to actually break the model.
It really does.
We're talking about huge systems, like GPT-5, just stumbling when you give them 10 million tokens. Researchers at MIT are even calling it context rot.
Yeah, it's the classic quality versus quantity problem. When you force that much data into a standard transformer's attention mechanism, the signal just gets lost in the noise.
So it's not just forgetting things.
No, it's worse. Its whole ability to reason just collapses because it's trying to pay attention to literally everything at once.
Okay, so the solution from MIT isn't about building a bigger brain. It's about changing how the brain accesses information.
Exactly. They're proposing something called Recursive Language Models, or RLMs.
Right, but this is the part that feels strange to me.
Yeah.
The paper talks about treating the prompt less like text and more like a coding environment. That just sounds weird.
It does sound a bit counterintuitive, but think of it like this. A standard LLM is like someone standing at the door of a massive library trying to memorize the spine of every single book all at once.
Okay, I can see how that would fail. The pixels would just blur together.
Precisely. Now, the RLM is more like a researcher who's already inside that library sitting at a desk with a laptop.
They're not memorizing the room.
Not at all. They walk to a specific shelf, pull down one book, read a single page, take a note, and then put the book back. The coding environment is just the laptop.
So it's not a chat box anymore.
Yeah.
The AI is basically working inside the coding terminal.
That's the technical reality of it. The RLM loads all that text as a variable inside a Python REPL, a read-evil print loop.
And that lets it write code to interact with the data.
Yes. It can split the text, peek at certain lines, and this is the crucial part, it can recursively call itself. It spins up these little submodels to process specific chunks.
But hold on. If the researcher doesn't memorize the library first, how do they know which shelf to even walk to? Isn't the model just flying blind?
That's where the coding part is so clever. It writes little scripts to scout the territory first.
Okay.
Take the Browse Comp Plus test from the paper. The task was to find the winner of a beauty pageant from a specific town festival, and the answer was buried in a stack of 1,000 documents.
Which is exactly where a standard model would just give up and hallucinate a name.
Precisely. But the RLM didn't even try to read all 1,000 documents. First, it wrote a reject script.
Regular expressions.
Right. To just scan for keywords like festival and beauty pageant. It's basically a keyword search.
So it's not reading. It's using Control-F to cheat its way to the right paragraph, and then it reads.
You can call it cheating, or you could call it efficient triage. That code immediately pointed to chunk 6 as the relevant section. Once it found that, the RLM triggered a recursive subcall, a mini-me, basically, and its only job was to read that one chunk. It extracted the winner's name, Maria Dalmacio, and then it even ran a self-verification step to double-check the year.
That distinction triage versus just reading, that has to be the key for more complex tasks. The paper mentions the oolong pairs test. I know that's a beast of a benchmark.
It is. It requires multi-step reasoning, not just fetching one fact.
Wow.
And this is where you really see context rot in action.
The base models just failed.
Completely. Models like GPT-5 and Qwen 3 coders scored near 0. They couldn't hold the chain of reasoning together. But the RLM wrapper,
It works.
it shot the score up to 58%.
Wow, from 0 to 58. But I have to play devil's advocate on efficiency. If it's writing code, running searches, spawning subagents, isn't that burning through compute credits like crazy?
Surprisingly, no. It's often cheaper. Because it filters the context with code before it commits the expensive neural network to reading, it avoids processing millions of totally irrelevant tokens. Think of it like skimming a table of contents versus reading the entire encyclopedia.
So we're moving past this idea of an AI as just a passive reader that gets overwhelmed.
We are. We're changing the definition of context. It's not a memory limit anymore. It's a resource to be managed. The model isn't just predicting the next word, it's investigating the prompt.
That feels like a fundamental shift. We always thought reasoning emerged from reading enough text, but MIT seems to be showing that reasoning might actually emerge from deciding what to read.
And that leads to a really provocative thought. If these models are now writing code to debug their own understanding of a prompt, are we maybe witnessing the beginning of genuine recursive agency in AI?
A lot to think about next time you see that chatbot typing animation. Thanks for diving in with us today.
Okay, so for today's deep dive, we have this. Well, this really fascinating paper from Sakana AI and MIT, it's called The Digital Red Queen.
Which sounds super
It
dramatic.
does, right. But the methodology behind it is actually, I mean, it's just incredibly clever. They're using LLMs to play a game.
An old-school programming game from 1984, Core War.
Exactly. And the whole idea is to watch how AI can, autonomously evolve software that is literally fighting for its own survival in a digital arena.
And Core War is a brilliant choice for that. It's not just some retro game. It's a Turing-complete sandbox. You have these little programs, they call them warriors, written in this assembly-like language called red code.
And they just get dropped into this shared memory space. The goal is, well, just to be the last one standing.
That shared memory is the key part.
Right. And, modern computers, you have memory protection. Your browser can't just go and crash your operating system.
Not in Core War. Code and data are all mixed up in the same space. The paper calls it a volatile environment.
So to win, your warrior has to literally rewrite the opponent's code on the fly.
While they're trying to do the exact same thing to you, the main attack they mentioned is called bombing.
Which is basically just, what, scattering junk data everywhere?
Yeah, you just drop these DFT instructions, garbage data all over the memory.
Yeah.
If the other program's execution pointer hits one, it crashes. Game over.
It's like digital gladiatorial combat. And you see these cool survival tactics emerge, like replication.
Copying yourself somewhere else to survive an attack.
Or scanning to try and find the enemy before they find you. It's chaotic.
And that chaos is where the Red Queen idea comes in. The researchers knew they couldn't just train an AI to beat one specific opponent.
Because that creates what they call brittle specialists, right?
Yep.
An AI that can win one matchup but is useless against anything else.
Precisely. So they used the Red Queen hypothesis from biology, the idea that you have to run as fast as you can just to stay in the same place.
So constant adaptation is the key.
Exactly. So instead of a static target, they made the AI compete against all the previous versions of itself.
That creates an arms race.
It's a perpetual arms race. The warrior from Generation 10 has to be able to beat the warriors from Generations 1 through 9. It forces it to become a generalist.
But doesn't that risk getting stuck? Where you just end up in a cycle, rock beats scissors, paper beats rock, and so on.
That's a classic trap in evolutionary algorithms. To get around it, they use something called MAP elites. Instead of just keeping the one best warrior, it keeps a whole diverse library of high-performing warriors that all use different strategies. It stops the gene pool from getting stale.
And that diversity is what led to the big aha moment of the paper.
This was my favorite part, convergent evolution.
Okay, so explain that.
They ran the whole experiment multiple times from scratch. The final warriors had completely different source code. Their genotypes were unique.
But their behavior.
Their phenotypes, converged on the exact same winning strategies.
It's like how nature invented the eye several times independently in different species. The underlying code is different, but the solution is the same.
That's the perfect analogy. The AI, on its own, figured out that the best way to win Core War is to maximize your number of threads and minimize your memory footprint.
That's incredible. And they could even predict how well a warrior would do just from its source code, without even running the battle.
Yeah, just by analyzing the text embedding.
Yeah.
They found the meta of the game purely through evolutionary pressure.
Which takes this way beyond an 80s programming game and drops it right into the world of, say, cybersecurity.
It's a perfect simplified model of it. The constant battle between hackers and defenders, viruses and immune systems.
This research shows that you could, in theory, get an LLM to just navigate that arms race on its own, finding vulnerabilities, patching them.
Or exploiting them. Faster than any human team ever could.
It's the ultimate double-edged sword. Using this, we could build software that's practically unhackable.
Or we could create malware that evolves in real time to defeat whatever we throw at it.
And that evolution happens at machine speed, not biological speed.
Exactly.
It's a sobering thought, really. It's one thing to watch programs fight inside a computer's memory. It's another thing entirely to imagine that same evolutionary pressure let loose on the software that runs our actual world. Something to think about. Thanks for joining us on this deep dive. We're all sort of used to this idea in the AI landscape that intelligence, well, it costs billions of dollars and needs its own power plant.
That's been the orthodoxy, yeah. The scaling laws.
The rule has been simple. If you want a smarter model, you just build a bigger model.
More parameters, more GPUs, more data. It's a brute force method that's worked for years.
But I've got a research paper here from NVIDIA that really challenges that whole idea. It's about a new family of models called Nemotron-Cascade.
And they're small.
They're tiny. We're talking 8 and 14 billion parameters, but they're apparently outperforming these giants with over 600 billion parameters. So our mission for this deep dive is to figure out how. How does the student model end up beating its teacher?
It all comes down to how the model learns, not, just how much data it eats. The paper introduces this strategy they call cascaded reinforcement learning.
Which sounds a lot more structured than the usual method.
Oh, absolutely. Usually you're just throwing everything, poetry, Python code, math, into one giant messy soup.
Yeah, and hoping for the best.
Exactly. And that noise makes it hard for the model to really generalize well. NVIDIA's Cascade approach is sequential. It's a pipeline.
Like a curriculum.
Precisely. They train it strictly in order. First comes instruction following, then math, then coding, and finally software engineering.
Okay, I see the logic, but usually when you teach a network like that, you hit a wall called catastrophic forgetting.
Where it forgets the old stuff.
Right. If you make it code for a month straight, does it forget how to be a helpful assistant? Did that happen here?
And that is the most surprising thing in this paper. Not only did it not happen, they found the opposite. They found a positive transfer.
A positive transfer.
The very first stage, the alignment with human feedback, or RLHF, it actually made the model better at math and coding later on.
Wait, hold on. RLHF is usually just about making the model polite, not saying harmful things. How does learning manners help you solve an equation?
It's not about the politeness, it's about the conciseness. The alignment training basically taught the model to stop rambling.
It reduced verbosity?
Yes. By forcing the model to be clear and token efficient, it decluttered its whole thinking process. And that clarity translated directly into better performance on logic problems.
That's a fascinating takeaway. Brevity as a form of reasoning. So let's talk results. You mentioned it beat the teacher.
It did. They used DeepSeek R1-0528, a huge 671 billion parameter model, to generate the training data.
So that's the teacher.
That's the teacher. And the Nemotron-Cascade 14B model, a fraction of the size, outperformed it on major coding benchmarks like LiveCodeBench.
And I saw the 14B thinking model even grabbed a silver medal at the IOI 2025.
The International Olympiad in Informatics, yeah, which is a huge deal.
So how did it pull that off?
They used a strategy called test time scaling. Instead of one shot, it generates multiple solutions and then picks the best one. But for me, the 8B unified model is actually the bigger breakthrough for everyday developers.
Because of that toggle feature, right?
Exactly. Usually you have to choose. Do you load the heavy reasoning model that takes ages or the fast chat model?
And you can't have both.
Well, the Nemotron 8B unified does both. You just add a think flag to your prompt for deep reasoning or nothing for a quick answer. It switches modes instantly with no performance hit.
Okay, that brings us to their final exam. Software engineering. This isn't just writing a function, this is fixing real bugs in a code base. How did they tackle that without some massive, complex agent?
They went agentless. Instead of a complicated loop of planning, using tools, reflecting, they just simplified the task.
Into what?
3 steps. Localize the bug, repair the code, and then validate the patch. But the really clever bit was how they trained the repair model.
Because grading code is slow. You have to run the tests.
Right. It's a huge bottleneck. So they built what they call an execution-free reward model.
Execution-free?
They trained a separate, smaller model to just check for semantic similarity. It looks at the AI's proposed fix and compares it to a known good patch.
So they essentially taught an AI to vibe check the code instead of running the compiler.
That's a great way to put it, yeah. It allowed them to scale up training massively, because they weren't waiting around for test suites to run. And it works. It's state-of-the-art for a model of its size.
It really seems the big lesson here is that maybe we've been too focused on size, on scale.
When we should have been focusing on the lesson plan.
Exactly. By structuring the learning logically, by teaching it to communicate clearly before asking it to code, they've shown you don't need a supercomputer to be best in class.
It's smarter training, not just bigger models.
And here's a thought to leave you with. This study proved that removing verbosity, just cutting out the fluff, made an AI's raw logic better. If that's true for a machine, how much is over-explaining and rambling hurting our own human problem-solving?
Something to think about.
Thanks for listening to this deep dive.
All right, let's dive in. I think we're definitely past the point where we just high-five an AI for getting one answer right.
Oh, absolutely. It's so much more complex now.
We're dealing with these multidimensional goals. We need the model to be accurate, but also, concise.
And maybe output a specific JSON format all at the same time.
Exactly. It's a huge balancing act. And that brings us to this new paper from NVIDIA and some others, GDPO.
Right. Group Reward Decoupled Normalization Policy Optimization.
It's a mouthful, but the mission here is pretty critical. They're basically saying the industry standard method, GRPO, is, well, it's breaking the training signal.
Breaking is a good word for it. The paper really focuses on this one specific problem they call reward collapse.
Okay, reward collapse. What does that actually mean?
It all comes down to how we add up the scores. In the standard approach, GRPO, you take your different rewards, say one for accuracy, one for being brief.
And you just sum them up.
You just add them into one big number. And that's the trap. Because you're ignoring scale variance.
It's scale variant.
Yeah, imagine your accuracy score is just a 0 or a 1, correct or incorrect. But your brevity score might be on a scale from 0 to 100.
Ah, so the brevity score just completely drowns out the accuracy score.
Exactly. The model learns really fast that the easiest way to get a high reward is just to focus on that big number and pretty much ignore the small one.
So it flattens the signal. It's like you
Yeah.
lose the resolution on what actually matters.
You do. You lose it. The paper calls it a low-resolution training signal. And once you've mixed it all into a smoothie, you can't taste the individual ingredients anymore.
So how does this new approach, GDPO, fix that?
Well, the key is right in the name. The D is for decoupled.
Decouple.
Yeah, so instead of summing everything first, it decouples the rewards and normalizes each one independently, based on its own little distribution.
Okay, so you're putting them on a level playing field before you combine them.
Precisely. The reward for accuracy is judged against other accuracy scores. The reward for brevity is judged against other brevity scores. Nothing gets drowned out.
And the results they show in the paper are, well, pretty stark, especially for tool calling.
Oh, absolutely brutal for the baseline model. They tested this on Quinn 2.5, asking it for these really rigid formats.
And in tool calling, if you miss one bracket or one comma in the JSON, the whole thing just breaks.
It's not just bad style, it's a runtime error. And the paper mentioned that the standard model sometimes hit, what was it, 0% compliance?
0. It literally couldn't learn the constraints because the signal was just too noisy. But GDPO consistently nailed the syntax.
Right, it turns a potential crash into valid code.
They also ran this on the AA math benchmark with DeepSeek R1. This is the one that really caught my eye because they were testing accuracy and conciseness.
And this is where models love to find cheat codes.
You mean it just optimizes for the short reward and tanks the correct reward?
Often, yeah. The easiest way to be short is to output nothing, or just some nonsense. It games the metric.
Yeah, GDPO stopped that.
It did. It improved accuracy by up to 6.3% while keeping the answers concise.
And a 6.3% jump on a math benchmark is not a rounding error. That's a huge leap.
It is. It shows the model isn't just compromising. It's actually getting smarter at balancing those trade-offs.
So what's the big takeaway here? It feels like we're realizing simple arithmetic just isn't enough for complex alignment.
I think it proves that you can't just average out your problems. If you want a model to be multifaceted, you have to preserve the distinctness of each goal during training.
Which, leaves us with a pretty heavy question to wrap up on. If the math is this tricky just to get an AI to balance being right versus being short,
Yeah.
what happens when we try to align these things on dozens of really complex, really messy human values all at once? Like safety versus censorship or helpfulness versus harm.
Does the math even hold up then? Or do we need an entirely new paradigm?
It's something to calculate on your own time. Thanks for diving in with us.